Hello everybody and welcome back to Algebra 2. Today we're going to be talking about 3-3 Systems of Inequalities. Let's get started. So first things first, like always, we're going to start off with the vocab review portion. So let's complete each statement with the correct word or phrase from the list below. Use each word or phrase only once. We got minimum, greater than or equal to, at least, or at most. The Florida football team needs, at least, 2 more wins to clinch the division. Now that we use that, we can cross this off the list. The blank speed a car may travel on the Florida freeway is 40 miles per hour. The minimum speed. Again, cross that off. If you have $45 and sweaters sell for $20 each, you can buy, at most, 2 sweaters. And last but not least, the height of a rider must be at least, or also known as greater than or equal to, 42 inches in order to ride the summit plummet. All right. So we have our first vocabulary builder portion, the inequality. An inequality is a mathematical statement indicating that one quantity is less than or equal to a second quantity. And notice it's okay for them to put less than or equal to because that also implies the opposite form, because if one is less than, then the other is greater than, and if one is less than or equal to, then the other would be greater than or equal to as well. So let's place a check next to the math statements that are inequalities, also known as anything that doesn't have an equal sign. All right, place an X next to the math statements that are not. Well, the very first one, we don't see an equal sign, so we know for a fact that that is going to be, in fact, an inequality. Again, the second one, we do not have an equal sign, so it is an inequality. This one is a not equal sign, which, again, isn't an equal sign. Therefore, it's an inequality. And last but not least, we do have an equal sign, so this one is not going to be considered an inequality. This one's actually going to be considered an equation. Complete each inequality with less than, greater than, less than or equal to, or greater than or equal to. If y is less than 6, therefore 6 must be greater than y. If b is greater than or equal to 10, then 10 must be less than or equal to that b. In other words, if we flip it around, we're also going to be flipping around that sign. So last but not least, we have r is going to be less than or equal to s plus t. So s plus t must be greater than or equal to r. Write an inequality symbol to represent each verbal expression. P is at most 10. That means the highest you can possibly go will be 10. Therefore, it must be less than or equal to that 10. So P is less than or equal to 10. U is greater than M. Well, that says it for you. U is greater than M. Remember, the greater than symbol ends off that G portion in greater than. All right, and last but not least, Z is at least 9, which means that the lowest number that we can possibly get is 9. Therefore, it's going to be everything after it, meaning it's going to be Z is greater than or equal to 9. Great work. Problem 1. Solving a system by using a table. Assume that x and y are whole numbers. What is the solution of the system of inequalities? Well, notice, this is just a standard system question. There's nothing really any different than the previous one. Instead of it just being equal to signs, we now have, inequality signs. So circle the inequality that has a finite number or whole number solutions. Part 10. Circle the inequality that has a finite number of whole number solutions. We have x plus y is going to be greater than 4. And then we also have the 3x plus the 7y is going to be less than or equal to 21. Well, remember our whole numbers can never be negative. And therefore, we're going to be talking about either the numbers that are strictly going to be above that positive 4, which means that we're just going to become farther and farther positive, or we're going to be talking about the numbers that happen to be less than or equal to 21. And in this case, if it's less than or equal to 21, eventually the numbers that we're going to be plugging in for the x and the y will happen to have to be, negative. So the numbers that we're going to have to be plugging in eventually will be negative in order to allow this to continue to be true. So if we had to circle which one is going to be the finite number of whole number solutions, I'm going to go and circle the 3x plus 7y has to be less than or equal to 21, because our answers are allowed to be less than 21, which means they're allowed to be negative. Whereas every single one of our answers for this one has to be greater than 4, which means it always has to be positive. 11. Use the inequality circles in exercise 10 and the whole numbers to complete each table of values. If we plug in a 1 for this x value right here, you'll get a 3 times a 1 plus a 7y is going to have to be less than or equal to 21. Well, if we continue to just keep on going down, we'll get 3 plus 7y is going to be less than or equal to 21. We then can subtract the 3 to both sides, and you'll get a 7y is going to be less than or equal to 18. 21 minus 3 is 18. And then we're going to divide everything by 7. Now, y has to be less than or equal to anything that is below or equal to that 18 over 7. So if we're only going to be basing everything off of the whole number portion, that means we can't have any negatives. That's why we start off with a 0. But more importantly, we only have the 1 because we're not talking about any decimals. 18 over 7 is in fact a decimal. Now, we do have to get one more number, so we have 0, 1, and then there should be something else after 1, so my guess would probably be 2, just out of curiosity, but I'm going to say that if we were to multiply the denominator by 2, you'll get that 14, it would be the denominator. Now, 18 is slightly larger than 14, but if we were to add 7 more to it, that would cross over the 18 mark, meaning that we would get 3, because 21 divided by 7 is 3, and 18 is less than 21. 14 divided by 7 is 2, and that is 18 is somewhere after that. So we know it's going to be in between the 2 and the 3. So we know that we can also include 2 as our another whole number. Well, if we use a 2 value, we can then just start plugging everything in. And again, you can kind of see based off of the boxes which values we're going to allow. So we have a 0, we're going to get a 1, as well as the 2 will work. All right, and that's because you'll have 21 minus 6, which is 15. Again, the 7 times 2 is only 14. 14 is going to be still below that 15 mark, so we will allow that too. But if we do 3 times 3 is 9. If we subtract that out, you get 12. 12 is below 14, so we know that the 12 divided by 7 will end up being somewhere between the 1 and the 2. And then we have our 4, which is going to turn to a 0, 1. Once again, and then we have 5 is going to be 0, 6 will be 0, and then 7 will be the final 0. And the reason that 7, 0 is going to be the final one that we can check is because if we were to plug that in, you'll end up getting, is because if you were to plug that in, you would get 3 times 7, and then we add that to our 7y is going to be less than or equal to 21. Well, we'll get 21 on the left-hand side. And when you have that 21 on the left-hand side, we have to subtract it to the other side. And you'll get 7y is going to be less than or equal to 0. And everything after this will turn into a negative that we work with. So if we divide that by 7, you'll end with that y is going to be less than or equal to 0, which is why we have it right here. But more importantly, if I were to plug in an 8, you'll get 3 times 8, which is 24, and as you can see in the first attempt and the second portion that we plug in, the very next step that we do is we would subtract that 24 from the 21, which would give you a negative 3, which we can't talk about because it needs to be whole number solution. So it needs to be not only no decimal, but can't be negative either. Part 12. Write the ordered pairs of values from the table that satisfy the first inequality. Well, from what I can see, we can just pick any of these, right? So we could do 0, 1, 2, 3, or we could do 1, 0, 1, 1, 1, 2, 2, 0, 2, 1, 2, 2, because all of these will work. So let's see what they ended up choosing. They chose 4, 1, which is on the list. They chose 5, 0, 6, 0, 7, 0 are also all on the list. So they're just basically pulling the points from this chart. Problem number 2, solving the system by graphing. Now, normally with an equation, we would just simply figure out where they cross, right? And if they cross, that is going to be the portion that we consider the solution. However, when you're talking about any sort of inequality, we also have to do that shaded region, which you can kind of start to see down here. And in that shaded region, where they overlap, like for this portion, it'll be right here, right there, and right here. These would also be the correct solutions. It's more importantly where they actually cross paths when it comes down to the shading portion, as well, obviously, as the line. If, of course, the line is solid instead of dashed. All right, well, in this case, both of these lines are solid, so we can't eliminate anything else out. But taking a look at this, let's figure this part out. So 13, circle the equivalent system that shows the equations in slope-intercept form. Well, we already have one in slope-intercept form right here, so we need to look for anything that has the y is going to be greater than or equal to the negative x minus 1, and sadly, they all have those. So we need to solve the top portion for y. So we get x plus 2y has to be less than or equal to 4. I'm going to subtract the x to both sides, but I'm going to keep it in that y equals mx plus b form portion. So I'm now going to have a 2y is going to be less than or equal to a negative x, keeping the negative with the x, but I'm going to add it to the 4 because that 4 originally was positive. Divide that by 2, and more importantly, divide everything by 2, and you'll get y is going to be less than or equal to a negative 1/2, because 1 divided by 2 would be 1/2, x plus 4 divided by 2, which is 2. So we need to find which one has the negative 1/2 x plus 2. And as of right now, we don't see any of those right there, but we do see it. Well, this one's not going to be it because that's a negative 2, but we do see two different ones that have 0.5. So I'm going to actually cross this one out because although it is close, it's not y by itself. So we know it's either the first or the third. Well, what's the difference between the first and the third? Well, if we're going to be talking about this, we have the less than or equal to sign. We didn't flip that sign. This one did, so we can actually cross this one out. So the one that we're going to circle is the third choice. Which one of these graphs shows this? Well, as I can tell, right off the get-go, both of our slopes are negative, which means both of our lines are actually going in a downward motion, meaning from left to right, it's going to be going down. That is how I would look at this one right off the get-go, seeing how we have two different graphs that are set up going in opposite directions. This one right here, the red graph is going clearly upward. That's positive slope with a negative slope in the blue. Again, the red right here is positive with the blue being negative. But the only one that seems to be going down in both attempts is going to be the blue negative and the red negative of the third graph. Therefore, I'm going to circle that graph. Problem 3. Using a system of inequalities. A pizza parlor charges $1 for each vegetable topping and $2 for each meat topping. You want at least 5 toppings on the pizza. You have $10 to spend on toppings. How many of each type of topping can you get on your pizza? We have to kind of figure it based off of the different variables that we're given. So we have the number of vegetable toppings plus the number of meat toppings is at least 5, because we need at least 5 toppings, right? It tells us that right there. So the cost of the vegetable toppings plus the cost of the meat toppings is going to have to be no more than $10. So we can't go above $10. So instead of it being at least, it's going to be at most $10. So let's start plugging in. The number of vegetable toppings, or V, plus the number of meat toppings, or M, has to be greater than or equal to 5, because that's what we're going to bring down straight from there, right? Knowing that fact, we then have to add in the cost. Well, $1 for every vegetable topping would look something like 1V, so I'm going to plug in a 1V. And it's okay if you don't put a 1 right in front of it. It's not going to change the answer anyway. All right. But the cost of the meat, however, is $2. So it's going to become 2M, 2 times the number of meat toppings. All right. And that is going to be at most, which instead of at least being greater than or equal to, at most becomes less than or equal to. And we're going to bring down that 10 value as well. There you go. So circle the inequalities that is equivalent to the system in exercise 5. Well, what can we see? We have one that says V plus M has to be greater than or equal to 5. So the very first one starts with a V plus M is going to be greater than or equal to 5, which does match up. But if we were to subtract that V over, We would almost think that this would work, but notice that they did change the sign, and we can't change the sign, so we can actually immediately rule out the middle portion, and the last portion, if we subtract over the v, still would work out fine as of right now. So let's take a look at the second portion. Well, if we subtract the v on the bottom to get to the 2m by itself, you would have a minus v over here. So the first one is not going to work, which means that if we were to solve it out, you would subtract over the v, which they did. We have a negative v right there. And if you were to divide everything by 2, you would get a 1/2 because it would be 1 divided by 2. Then you'd have the 10 divided by 2, which would equal the 5. So the last system is the correct system. So let's circle the types of numbers that can represent the number of toppings you can get on your pizza. Well, that could be the rational numbers, meaning anything that involves any sort of decimals. I can't really have a decimal, right? And therefore, I can kind of rule out rational. Integers are all counting numbers or whole numbers, but the difference is you can have negatives. And last I checked, we can't have a negative pepperoni. Right? Whole numbers are going to be anything that is like counting numbers, which is going to be 1, 2, 3, 4, 5, and so on and so forth up, and it includes 0, right? And therefore, right here, I'm starting to think that that whole numbers is correct, because you can have that many types of toppings. And then the real numbers includes everything, decimals, negatives. It's going to also have irrational numbers as well, which is a fancy type of decimal. So I know for a fact that real numbers will not work, so the correct one will be whole numbers. Use the graph of the system at the right. Underline the correct number to complete each sentence. If you order 0 vegetable toppings, you can order at most, well, if we had 0 vegetable toppings, that would mean that we would have to go all the way to the 0 on the x value, or on the x-axis, because that's what's labeled vegetable toppings. And I'm going to say that the most that we can get will be 5 meat toppings. Well, if you order 10 vegetable toppings, 10 all the way over here, it looks like we can only have, well, actually it looks like we can't even have a single form of meat topping. So it will be 0 meat toppings at most. And the most important part is if we were to figure out which one of these will actually end up working, and we did want to have a combination of the vegetable and the meat, you can start paying attention to the integers that happen to be following through any part of this double shaded portion. Right? All of these will allow to be true. Problem 4. Solving a linear absolute value system. It's done the exact same way as solving a standard system. The only difference is we have an inequality sign that is attached to an absolute value portion. Well, we can still do the shading and everything the same exact way. We can still graph it the same exact way, so it's really no different. So the graph that is given right here is on the right. Let's just figure out where we have to actually, well, darken in. So the graph at the right shows the boundaries of the system. Shade y is less than negative 1/3 x plus 1 vertically, and shade y is greater than 2 times the absolute value of x minus 1 horizontally. Right? Darken the region of overlap, then label each inequality. Well, it looks like we already have everything pretty much set up for us. We just need to figure out where are we going to darken in. Well, taking a look at that very first, the linear function, which is going to be this blue straight line. All right, and I'll even write that this is the blue portion, and this is the red portion. All right, the blue portion is going to be shaded below the line, so it's going to be everything underneath. So I'm going to be shading everything down below, whereas everything on top of the line or inside the cup, as you will, for this absolute value will be shaded in. So I'm going to be shading in the top portion like so. So it's on the inside, everything above this line, and then everything below this line. And now the most important part is the region that overlaps. You'll notice that the only spot that these things actually work out to be true is going to literally be right here. Everything else outside this tiny region is actually considered not a solution. The only spot that's allowed to be considered a solution is where both of the shaded regions hit, which is this spot right here. And we finally made it to the lesson check, guys. So, is the solution of a system of inequalities a union or an intersection of the solutions of the two inequalities? Justify your answer. In other words, are we going to be talking about things that are going to be touching one another, going in between, or are we talking about the things that go outward from one another? Well, the system of inequalities are similar to the system of equations, although that is true. The solution of a system of equations is the union of all points on the graphs of the lines. Well, that's false. That's not necessarily true. The solution of a system of inequalities is the union of all points on the graphs of the inequalities. Once again, that's false. That's not necessarily true. So my answer for this problem will be simply the solution of a system of inequalities is the intersection of the solutions of the inequalities. In other words, it's where the shaded regions have to be touching. It cannot be the shaded regions that are completely away from one another. To put it into better perspective, I'll draw two different graphs. We have the one right here and we have the one down there. If they're going to be considered intersecting, it would be like having a graph like this, but more importantly, the shaded region that we're talking about is going to be everything in this top corner. All right, and that is going to be the intersecting portion. Whereas in a union, when you're talking about the union portion, it's going to include everything. So if I shade this direction right here and this direction up here, a union would include this portion of the graph. It'll also include this portion of the graph as well as the third portion, but it just will exclude this portion on the left-hand side. However, the true solution is only where they intersect. Alright, it's only this first portion right here. And that is it, everybody. Great work. I hope everyone has a wonderful day. Stay out of trouble. Don't do anything stupid. And I'll see you guys in the next one.